Is your coffee ready? I hope so. The delicious cappuccino is ready for another paper. This time we're gonna talk about IRISformer, which translates to dense vision transformers for single image. So iris comes from inverse rendering of indoor scenes, and former comes from transformers, which is the new trend in computer vision that came from language domain, and it's taking over everything in computer vision, or at least most of tasks lately are being done with this new method. So let's see how this impacts the domain of inverse rendering. So just a quick recap of what is intrinsic image decomposition. So basically in this task you have the image here on the left that has to be decomposed into the original components of the scene. So what you have here is an image made of pixels, but each pixel is basically a combination of a 3D layout, emitters, which can be ceiling lamps, can be windows, and you have also 3D objects. And those 3D objects themselves have many characteristics. For example, the reflection, their roughness, and same thing goes for the emitters. They have different parameters, and the layout as well. So as you can imagine, a pixel here, which is a single color, is actually the result of many interactions. So this task here of intrinsic image decomposition is really hard because of this nature of the problem, where you have, for a single pixel, many components that work together. And usually what happens is that many different combinations of lights and objects can generate the same pixel color, so it's really challenging. But there are many methods being proposed in the few last decades, and recently there's been a huge advance in this field, and let's see today what transformers bring to the table. So in this paper, what they propose is to do exactly that, intrinsic material scene decomposition. And in their case, they propose to infer the material, which is given by the albedo and the roughness, and the geometry by depth and normal. And then you have a lightning representation. In their case, is especially varying and is presented as spherical Gaussian mixtures. And why do we talk about vision transformers? Because basically that's the novelty of their approach. So all this here, it's already been proposed in the past, how to decompose the image. Even this lightning here, it's not new. So all this is not a new domain, but trying to solve this with transformers, that's where the fun begins. So let's see how they perform that and why transformers for this problem in particular. So here there's the teaser of the paper. You can see that you have the input image, and those are the results. So you have 4 different outputs, the albedo, roughness, normals, and depth. There's also lightning, but it's not being shown here. And as you can see, compared to previous works, you have a much sharper division between, for example, the walls and the floor, both for albedo and roughness, also normals, depth. So you can see that in general, the results are better, and according to the authors, it also comes from the design choice of using transformers, because transformers, they can use global information better than CNNs. I'm gonna go quickly through transformers and try to make this more intuitive, why that's so. So what you get from their estimation is a render that looks more realistic. So you can see here that the shadow has a better appearance of the object that is being inserted compared to previous work. In fact, this work here is not bad at all, but in this case here you can see the reflections may be better represented in the object. And you have this reflection here that maybe you may see it's better than this one. So all this combined gives us a better idea of what's going on. But I would say those are the results that appear more appealing, because you can see in individually each estimation and how it compares to previous work. And as I said before, the whole thing about transformers that I'm gonna talk more in a few seconds is that you have the attention, which is better distributed compared to previous CNNs. So usually CNNs, for example, if you take this pixel here, a CNN would be able to look to nearby pixels, and as you go further away from the pixel, this heat map would become less evident. So probably the CNN would not be able to look at this portion here, simply because it's too far from the pixel. But transformers, they have another way of looking at the image that makes possible for a single pixel to see everywhere else and pick the regions of the image it sees, it thinks it's important. So let's see how that goes. To explain this paper, the best way to go is, well, to go to the previous papers. In our case, we have to go to the dense prediction transformer, which is one of the first papers to propose to use transformer to do dense prediction in an image. But to understand this one, you have to go a little bit further away, which is the vision transformer, which is the first paper that used transformers for a vision task. And then we go finally to the transformer itself. Then we go out of the image domain and we go to text, where this technique was proposed. So let's start. We're gonna do this way, because then by going from the transformers all the way up to the DPT, we basically get IRISformer for free. If you're already familiar with intrinsic image decomposition, it's not a big leap. It's just understanding how transformers work, and then you get IRISformer. So let's start with the attention is all you need. This is a paper that really changed many areas, including computer vision. And here what you can see is the model that was proposed. And the whole idea is that you have a method that can not only look on the sentence that you want to translate, but also can look at the sentence that has been already translated. So for example, here you have this sentence here, the cat eats the mouse, for example. And you have its translation in German, let's say, die Katze. I'm taking this from Yannick YouTube channel, so that's why it's like I'm using his part of his video. So to see here what's going on, basically we have this model that is divided into an encoder, which is this part, and a decoder, this part here. So the encoder takes as input the original sentence. So the cat eats the mouse. So it goes here, and for each piece of this sentence, it's gonna have a input embedding. So basically it's just a multiplication of the sentence with this input embedding, and then you get a vector, and this vector is concatenated with something that's called positional encoding. So this positional encoding basically says where is the token that we are looking right now in the sentence. So you could argue that this could be a simple number saying, okay, I'm right now working with the third word of the sentence, so it should be just number 3. But the authors claim that this positional encoding allows the network to use this information in a better way. So it's more than just a number, it's a vector, so you just concatenate it and it becomes the input. And after they show what the positional encoding is encoded, and it's actually pretty similar to what you would expect. It's basically a heat map showing that like the position where the sentence is, but it also allows the network to say, okay, actually I'm here, but I can take close to this thing, close to this thing here, and it can like use this in a smarter way. So once you have this representation, you go into this module here, and well, there's some operations that are pretty standard, like add, normalize, feed forward, but the thing that's most important is the multi-head attention. So this module here is this part. It's here on the bottom, the attention. So for this attention, you have three inputs. You have key, Q, and V. It stands for query, this is key, and this is value. Well, I'm just rewriting them here. So you have query, key, and value, which means that you have a table of keys. Those keys, they relate to some value. And you have a query. So you have a query and you look where is it on the queues. Once you find the key, you go to the value that corresponds to the key. So basically what is happening here, you have a product between the query and the key. And imagine that the key is actually a bunch of vectors. So the first one points like this, the second like this, the third like this, the fourth like this. And the query is basically another vector. Let's say our query is like this. So by doing the product, the higher value will give us this key. So what you're doing is like globally you are searching for the key that matches best the query. Once you have this, you can take the value and then that's the value you're looking for. So that's basically what's happening, the attention. And this simple operation, it's really what's like the core novelty of everything here. And by doing this, you have this this value that goes out, and it goes to the output to the decoder. So I'm gonna just write D for decoder, E for encoder, and the decoder here takes this key and this value, and again it goes the key and value, and you have again another query, and you go on this with the output. So now you take the sentence that is the output, same here, you have the embedding, you have a positional encoding, and then you have this multi-head attention going on again. And with this you can not only use the input sentence but also the output sentence, and then the network can make sense of what is already translated to predict what's going to be translated next. So in a nutshell, that's the attention mechanism. And as I said, like it's super simple, but it's more general than CNNs because it can take global information into account better than a CNN for images. So actually, let's go and see how this can be done with images. So as you all know, images, they are not exactly like a sentence. They are more like this grid of pixels. So there's not really this relation of previous and next sentence. But this paper here, well, I don't have the reference here, but attention is all you need. It's the name. An image is worth 16 by 16 words. That's the name of the paper. What they propose is to split the image into patches. So you can do this 16 by 16, for example, and you treat it as a sentence. So it may sound weird, but as a first approach to use transformer, it already showed that it's already performing and outperforming CNNs in some tasks, in this case classification. So it's really impressive to have this kind of result with such a simple model compared to the super complex CNNs that we have these days. So what it does here is to take this image, break it into patches. Those patches, so they are flattened, so basically they are transformed into a vector. This vector is multiplied by a matrix, the embedding. So basically that's what's happening here. And then you have a vector again. And this vector is, as I showed before for the sentence, concatenated with a position embedding. So it's the same thing. You have again another vector that represents the position of the patch inside the image. And again, it's learnable parameter. The network is the one that decides. So you take this and you put it, for example, here, number 3. You put it here. And the positional embedding is this one. So you concatenate them and you send to the transformer encoder. So we don't have the decoder as for the text, because we don't have this notion of what has been translated and what has to be translated. We just have the encoder. So you embed, then as you can see, it's the same idea. You have multi-head attention, you have the query key values, and by doing this you can organize and have the whole, well, make sense of the whole image together. And in the end, what you had is a single multi-layer perceptron that does the task-specific job, which in our case is classification. In this paper is classification. So take the image and say what class it belongs to. Is it a bird, a building, a car, etc. So this is really mind-blowing, I would say, for computer vision researchers, because of such simple design can produce such a good outcome. And of course, there's something else that is why nobody think of this before. And I think the answer is that nowadays we have such huge amount of data that is making the networks less and less biased toward a specific problem. So CNNs, what's great about CNN is that the whole idea is that instead of having a feed-forward network where each neuron listens to all the other previous neurons, you have this bias that nearby pixels, they have more information that is useful for a particular pixel than like far away pixels. So what you do is that you construct the network in a way that the nearby pixels get more attention for a pixel that we're looking at. So we start here and then we look at this neighborhood, and then so this gives us, for example, a first layer of the network. And then on the next step we are concentrating information even further, so we look at a bigger neighborhood. So let's say this 4x4 bigger window, and so on. So here we start with really low level features, and here with high level features. But as I said, like this, the problem is that in the beginning of the network, it's not possible to look everywhere. There's no way to look globally. So each information here is actually coming from a very specific part of the image. So let's say this one here encompasses just information that is in this region. And actually what you want is go further away, right? So that's where transformers come and change the whole thing. And just another way to explain how transformers, they really give you this advantage, is to think about to see this figure here, taken from the paper. And here on the bottom you have the layer number. So you start from the shallow layer, the first layer, here 0, and you go up to 20, let's say. And 20 is so that the most high level features are here. So if you have a transformer and you look at the attention distance, you can see that at the beginning, the first layer, it can see all the, like a huge neighborhood. So let's say here you have this image of 120 by 120. It means that at the first layer can already watch and pay attention to pixels basically everywhere in the image. So this is really interesting. You can see that this behavior continues as you go deeper into the network. And what's different? So basically, if you have a CNN, you would see something like a line, a straight line. These pixels, this behavior here cannot happen with a CNN because it basically doesn't have the reception field to cover the entire image. So this is a CNN, and this is the contribution of the transformer. So that's the whole thing that's happening that didn't happen before. So it's really interesting. Just wanted to bring the attention to this again. And once you understand that, now we can go a step further and see another task in computer vision that uses transformer, which was proposed by this paper called dense prediction transformer. And dense because now we are not classifying the image, so it's not a single value for the image, it's a value for each pixel. So for example, here we have a depth estimation, so it's one prediction for pixel. So the basic idea is to take inspiration on this dense prediction networks, where they have this kind of pyramid design, where they start from like a big high level information, and they go and make it like smaller, more concentrated, and then they go back and inflate back to a image size. So what we have here is basically the same idea. We have the embedding part, and then we transform the image that was already split into patches. Then we get these tokens here, and also there's this like 0. The first token is basically like just to get like started with the transformer, and then you apply the transformers to each of those tokens, and you have an output like a different amount of tokens or different size, and then you keep going, and then you have this reassemble here, which is basically doing this kind of transformation. It takes the tokens, read them, concatenate them, project, and resample. So and then the output is this in this format, which is like an image. So basically a simple 3D shape. And then you have fusion, which is here, and then you have from the you take from a previous step and the current step, you concatenate them, you do a residual convolution, resample, and project. So basically what you're doing here is to reshaping them and adding them until you get here, and here there's a head, which is a task specific part of the network. So basically you can do this in generically, you can do this and apply for every dense prediction problem you have. And then here you have the head specific task. So in this case is depth. You can just change this head to semantic segmentation. So this is again amazing, because you can just come here and change the head and have another task which is really different and have really nice results. And that's what this paper shows. Like they have state-of-the-art results for many tasks by using this common model here. So this is really something that came as like a breakthrough, and probably it's like just the beginning of something, I would say, that is gonna again shake and change everything in computer vision. So it's really exciting. So once you understand this, we go to our actual paper, which is IRISformer. And now the good thing is that once you understand all these 3 previous papers, this one comes almost for free, because this is DPT, so dense prediction transformer, and you simply do it and have many heads. So instead of having just depth, you have now depth, you have albedo, roughness, depth, and normal. So everything else is basically the same. You have the encoders, which are the transformers, and then the decoders, which are the reassemble and fusion, and you have the output, which is specific. And in this case they have 2 options. They have the multi, so their network they call BRDF GeoNet outputs those 4 heads, and each head so give us a prediction of the specific modality that we are talking about. And they also have this single, which is a single head. Actually, sorry, there's a head that outputs a specific modality, but you have individual encoder and decoder for each modality. So you have 4 times this, and here you have an encoder decoder that does the whole thing with just different heads. So they propose to show the results for both and discuss the results for both. So this is the entire method. You can see here on the left the transformers and the heads, and no matter where it comes from, it goes all to this lightnet, which is the last part, and the lightnet outputs a lightning representation. So this lightning representation here, for those who are not familiar with, and it looks like funny, it's basically a way to say, if I'm here in this image and I place an object right here on this first pixel, what would be the lightning that is affecting this pixel in particular? So that's what we have here on the right. Each rectangle here is what we call an environment map, and it explains the lightning that arrives at this point in the image. So you have one prediction for every single pixel in the image, and this is represented by this mixture of Gaussians that are represented by these three values here. So one is like a bandwidth, the other is a frequency, the other is I don't remember exactly what it does, but you just look at what the Gaussian mixture, how it's represented, and then you have those three parameters. So in their case, I propose to have one head for each of the parameter of the Gaussian, and then you can render and have the light prediction like this. And then after that, you can position an object, place a virtual object anywhere in the image, and you just go and look at this table of lighting and pick the one that you want and use that to render the object at this position. And that's it. The paper is basically that. You have all this trained with a loss that is straightforward, is basically reconstruction loss everywhere. So you take the prediction compared to the ground truth. They train on a synthetic data set, and so they have ground truth for everything, and then they just compare the render with or the output of each head to the ground truth, and they compute a L2 loss. And here for the lightning, they have reconstruction. They render the image again, and they compare to what they had, and also they have the ground truth for lightning, so they can do the render the loss directly on the lightning. So that's it. The paper is really simple once you understand the individual blocks, but as always, like, it's a really nice contribution because the authors just took the idea of transformers and applied to a new domain, and this by itself is a contribution. So I could stop here and not even talk about the results, but of course we are interested in see them. But the contribution is to show what transformers can bring to this domain. So let's see what it happens. So here what we have is decimation on open rooms, which is the synthetic data set. And what you see is the albedo for previous work compared to their current. And they show for the multi and the single approach. So as you can see here, in this case, visually speaking, I would say that albedo is better estimated by the single approach. And roughness, it's hard to say. Honestly, I cannot decide, especially because, well, okay, here's the ground truth. So maybe again, the single is better because let's say this portion here is closer to the ground truth. We have depth, and we have depth before and after bilateral solver. So this is before and then it's after. And this is not a big difference. But you can see that previous work is much more fuzzy, so there's clearly something better going on here. And same thing for lightning and the re-render. So actually the re-render is a kind of tricky thing to analyze because basically the re-rendering can be super close to the input image, but simply because you are optimizing those to exactly reconstruct the image, but you're not taking this each into account to be realistic by themselves. So basically what I want to say is that the albedo can be something completely different, but then you use the roughness to compensate for the error in the albedo. So same thing for the depth and normals, and have the perfect reconstruction, but the individual predictions are really bad. So this is just a way to visualize what you get from them together, but as I said, it can be easily manipulated by the optimization method. So here there's not a big difference, and even you can see here that actually the window part is better reconstructed by this previous work, even though their individual reconstruction is not that good. And you can see that there's actually a lot of information here on the albedo, and well, it's tricky because here the ground truth albedo is completely black, even though there's information here, but probably because if it's a window, it's not considered as albedo. So yeah, that's probably a problem from the ground truth as well. So the network, it's hard to ask for the network something it couldn't access through training, during the training. Other result here is showing real results, so those are real images, so there's no ground truth for the individual components, but visually speaking we can see that again their prediction is much more sharp and consistent, especially depth. Here you can see that the table, it's here it's not showing at all. The roughness here also, it's interesting because you can see that the previous work applies a different albedo for the same object just because it's taking the reflection into account for the albedo, which is not what we want. And this new work shows an albedo that is, oh sorry, this is roughness, but yeah, it's the same thing. Roughness shouldn't be different for this object because it's the same material everywhere, and you can see the albedo is also showing this different albedo value even though it's the same object, and this new paper doesn't show that. So this is really, really interesting. And then we have for another image, and again you can see the albedo changing here, and it shouldn't, and here it's more consistent. And same thing for the roughness, the depth also, it's much better. So yes, you can see there's clearly improvement in this paper. Another result here we have from another data set, IIW, and for here we are just looking for the albedo, and also we are seeing here the normal and the depth. So again you can see that they have a better, well here there's a ground truth, so this is nice from this result. You can see that again this method is usually showing more consistency in pixels that are neighbors, and same thing here, like this part here gets picked, and previous work it was completely missed. So again, really encouraging. And finally some editing results. So here the authors insert this virtual texture into the wall, and they claimed like the results is better. Honestly, for me it's hard to judge because I think this is pretty convincing as well, and object insertion is kind of hard to have a fair comparison because it depends on so many factors. It depends on the rendering, depends on user preference. So this part here is really usually better analyzed if you take it and give it to a bunch of users that receive each image individually, and they have to rate which one they prefer. So by looking at a single picture, it's hard to say and choose the best, but in any case it's not worse. So I cannot say, well, this new one is worse. So it's a tricky result, but in any case it shows that the method can be used for object insertion. And here again, I'm just showing that the attention, now that you understand transformers, you can see that, for example, if the network is estimating, I think here it's albedo, you can see that this pixel here is having his decision taken by looking at all this region here, and which it makes sense for most of it. This part here shouldn't be taken into account completely, or maybe yes, because it's part of the wall, but this is really what we want, like take the information from this region and disregard, for example, this, even though it's super close, but it's not part of the same material. So that's the nice part of this attention mechanism. Here again, some other insertion results. So they basically inserting the bunny, comparing to previous work, Baron, which is kind of old right now. So it's, yeah, it has its contributions back then, but these days it's more like a baseline, and you can see the previous works. Again, to be really honest, personally, I think it's hard to pick a clear winner. Maybe we should need more images to show a trend. And saying that, for example, well, sometimes like I can say this bunny, for me particular, I prefer this render. So yeah, their paper is, I think it's the best on this. But here for me it's hard to say that this one is the best. I think here it's the winner, because this bunny here, it's better blended in the image, or even this one, but this one seems off, like it's shining, it's glowing too much. So as I said, like, this is a really hard evaluation to be made. It's, of course, it's really nice for the authors to show it here, but it's not something I would take into account from just a few images like this to have a final opinion about the approach. But as I said, the individual predictions were pretty good, and the renders can be tricky sometimes, because yeah, it depends on so many factors that sometimes they don't pay the tribute to the paper that they should. So yes, again, as I said, it's not like it's super bad. It's just that it's hard to evaluate. I think for this to be like a scientifically way to compare, it should have many papers, or sorry, many results being compared and given to a bunch of users and ask them to pick the best. And that's it. Thanks a lot, and I hope I see you next time. Bye.